Hi there everyone, and welcome back to week 11 of our exam countdown. So as you can see from the title here, today we're going to be looking at applications of differentiation. So we're going to have a look at a couple of exam questions, and I'm going to take you through some different things that can be asked. So before we start, as always, our full members, you're going to have access to a range of resources on our Maths Tutor website. And if you're not a full member, I have linked two videos in the chat. The first one is the 2014 question 9. It's an example of an exponential function and it has rates of change in there. And the second one, 2015 question 8, the oil spill question, and there are some related rates of change questions in there also. So we'll jump straight in, and you might remember the last day I mentioned all of these: dy dx, f dash x, slope of a tangent, rate of change, and the derivative. And I said that these were all different ways of asking us to differentiate. So they all mean differentiate. And as we get on to the more wordy problems, you're going to see rates of change being used quite a lot in a question, or slope of a tangent. So it's important to recognize they all just mean that we differentiate. Okay, you might remember the last time as well, we talked about max and minimum points. So if we looked at just a regular cubic function, we talked about the maximum, and we just drew a tangent there, and also the minimum point, and we drew a tangent there. As you can see, those two red lines, they're both horizontal lines, and they would have a slope of 0. So that would mean that my derivative would be 0 at a max and at a min. And I mentioned that we pick up marks in the exam questions for writing that. So at a max or a min, the minute we see that in a question, we remind ourselves that f dash x is 0 at a max or a min. So the derivative is 0 at a max or a min. And it's also important to remember that at a maximum point, your second derivative is negative, and at a minimum point, your second derivative is a positive number. So those are quite important when we're differentiating between max and min points. And we also mentioned just very briefly that at the point of inflection here, our second derivative is actually equal to 0 at that point. So the point of inflection is where the curvature changes from concave to convex, or vice versa. Okay, so let's jump straight in, and you're going to see lots of I suppose functions in here, and various different topics, I suppose, mixed in. Calculus or differentiation is always a huge part of paper 1 in the maths exam. So I'm going to do a couple of the more recent questions with you today, hopefully. And we're going to start with 2021, paper 1, and we're going to start with question 10. So, water is flowing into and being removed from a tank. The volume of the water is measured on a daily basis starting at day 0. The volume of the water in litres, so that's going to be important for when we put our units in the question, in the tank can be modelled by this formula. Okay, so just highlighting that, and it's telling us that the volume is always greater than or equal to 0. T is the time in days starting at day 0, and use that function to answer the following 4 questions. So part 1 asks us, find the value of T when the tank empties. Okay, so if we think about it, if the tank is empty, well, that means there's no water in the tank. In other words, your volume is going to be equal to 0. So it's empty. In other words, there's no water. And that would mean that our volume of water in the tank is 0. There's nothing in it. So we're simply taking our volume formula, which is 60 plus 41t minus 3t squared. We've highlighted it up here. And we're letting that equal to 0. So I'm just going to rearrange that ever so slightly. I'm going to bring the t squared to the start, the t in the middle, and the constant at the end, and it's equal to 0. And the reason I've done that is now we can recognize that that is how we more commonly see quadratic equations being written. And we're going to solve that quadratic. So you can use guide number or you can use minus b. I'm going to go ahead and use minus b. So that minus 3 is my A, 41 is my B, and 60 is my C. So I'm going to write my minus b formula over at the side of the page just to ensure that I'm picking up all the marks that I possibly can. And I'm getting that from page 20 of my log tables. And I'm just going to sub in. So I'm getting T is minus 41 plus over minus the square root of 41 squared minus 4 times A is minus 3 and C is 60. And that's all over 2 times A, so that's 2 times minus 3 in this case. So you're just plugging that straight into your calculator and you should end up getting two answers. One is going to be T is 15 and the other one should be T is minus 4 over 3. Now let's remind ourselves, T was our time in days. So obviously minus 4 over 3, it is one of our answers, but it makes no sense for time. So we're just going to reject that and we're going to accept our 15 days as our answer. Okay, so just to make it nice and clear, your answer is 15 days. So it takes 15 days or 15 days have passed when the tank empties, because remember it's flowing into and being removed from the tank, we were told. Okay, so nice and basic, just a function and we're solving a quadratic. Next question, part 2, find the rate. So the minute I see rate and changing, I'm thinking rate of change. So find the rate at which the volume of the water in the tank is changing at this particular time. So at day 5 or when T is equal to 5. So the minute I see rate of change, I know that it's going to be differentiate. So what am I differentiating? Well, I'm differentiating the volume. So I'm looking for V dash T. So I'm taking my function from up here. I'm taking my volume function from here and I'm differentiating it. So when I differentiate 60, a constant, that goes to 0. 41t, I just dropped the t, so I'm left with 41, and minus 3t squared. So I'm multiplying down by the power, minus 3 by 2 is 6t, and I'm reducing the power by 1, so it's 6t to the power of 1 there, if you like. And that is the rate of change, but we're interested in the rate of change when t is 5. So that's v dash 5 we're looking for. In other words, everywhere we see a t, we're going to replace it with a 5. So it becomes 41 minus 6 times 5, and that should give us 11. Think about your units. So it's the rate at which the volume is changing as time goes by. So the volume is litres, as we were told at the start. And in this case, our time is in days. So it's 11 litres per day. At day 5, the volume of the tank is changing at a rate of 11 litres per day. Okay, so a little bit of differentiation there. And part 3, find the value of t when the volume of the water is at a maximum. So straight away, I'm highlighting that word maximum and I'm writing down every time I see the word max or min, we know that at a max, the derivative, in this case v dash t, is going to be equal to 0. And just for writing that much, in this question, you're getting 2 out of 5 of the marks. So that's 40% of the question, just for recognizing the word maximum and writing the derivative is equal to 0. Okay, so we're going to take our derivative, which we've just found in part 2. That was 41 minus 60, and that was our derivative. At the max, that's going to be equal to 0. And obviously at the min, that will be equal to 0 as well. So solving for t, we'll end up with 41 is equal to 6t. And your t works out to be 41 over 6. And I'm just going to leave it as a fraction here. And of course, because it's time, in this case, it's time in days. Now, just to double check, that could be a max, it could be a min. So just to verify that it is a maximum, we're going to do our second derivative test. So we're going to find our v double dash t, or our second derivative. In other words, we're taking our first derivative, which was this one, and we're differentiating. So when I differentiate 41, it goes to 0. When I differentiate minus 6t, I get minus 6. And if we just remind ourselves of what we said up here, remember up here, we said that at the maximum, the second derivative, so there we are, at the maximum, the second derivative is negative, while at the minimum, the second derivative should be positive. So if we go back to our question, we've just gotten a negative second derivative, so therefore we're pretty sure, or we're confident that this is a maximum point. But your answer, of course, we're looking for the time in days, so your answer is 41/6. Okay, moving on then to part 4. Find the maximum volume of the water in the tank. So what we've just found out up here in part 3 is that the maximum occurs at t equals 41/6. So after 41/6 days, so that's just a little over 6 days, the maximum volume of water is in the tank. But we're looking for the maximum volume. So we're taking our volume formula and we're replacing the t with 41/6. So we're not subbing back into the derivative because that's the rate of change of the volume. We're just looking for the maximum volume. So your formula that you started with, which was 60 plus 41t, so in this case t is 41/6, minus 3t squared. So that's coming from the original question. So instead of t, all we've done there, as you can see, we've replaced every t with a 41/6. And you're subbing that straight into the calculator. We should be getting 200.083, and they're asking you to the nearest litre, so that's going to be 200, and our units are litres to get our full marks. Okay. So that is from the 2021 paper, and that was part of a long question. So it was a 50-mark question, but that's only half the question. The other half was not calculus, it was sequences and series. Okay. So we will move on and we'll get a chance to look at another question. So this one is quite a good one. Again, this is from 2021 paper, and this is question 9. So differentiation was a huge part of the paper last year, as it is every year for paper 1. Okay, so a cup of coffee is freshly brewed to 95 degrees. That's going to become important in a second. It's freshly brewed. So at the time we start the clock, I suppose, initially, it's 95 degrees Celsius. The temperature in degrees of the coffee as it cools is given by this formula. So that's the formula we're going to be working with. A is just a constant number, and T is time measured in minutes from when the coffee was brewed. So initially, at time equals 0, might be no harm to write that in for ourselves. When T is 0, the coffee is 95 degrees. And we're asked in part 1 to show that that constant A is 75 degrees. So we are going to remind ourselves that they've told us up here that when time is 0, so initially, because the time is measured from when the coffee was brewed, then your capital T, your temperature is 95 degrees centigrade. So we're going to use that and we're going to sub that in here. For our large T, that's going to be 95. And for our small t here, that's going to be 0. So it becomes A times e to the power of minus 0.081, and instead of small t, we're replacing that with a 0 here, as you can see, plus 20 is equal to, and instead of big T, we are subbing in 95. Okay, so we're going to solve that equation, and we're solving it to try find A, and we're expecting it to be 75. So what we've got here is we have A times e to the power of 0, basically, because anything times 0 is 0, so that will make this whole power 0. So A times e to the power of 0, and anything to the power of 0, we can check it by putting that into our calculator. Anything to the power of 0 is always going to be 1. So that's going to give me A times 1 plus 20 equals 95. And when you subtract 20 from both sides, you'll see that you're getting A is 75 degrees, or 75 is your constant A there. So from now on, when we're using this formula up here, we can use our constant A. We now know that it's 75. Part 2, explain what the value 20 in the formula represents in the context of the coffee cooling. Okay, so obviously as time goes by, the coffee is going to cool. So what we're going to do here, just to show you where the answer comes from, I'm going to use the formula. So that's temperature is, A was 75, e to the minus 0.081 T, and I'm going to sub in T in a second, plus 20. And I'm just going to sub in a really big number here for T. So imagine that the coffee was sitting there for, just going to say randomly, 180 minutes. Okay, so it's sitting there quite a while, it's sitting there about 3 hours. And we're going to see what we get when we put that straight into the calculator. So it should be giving you, and we're putting it straight into the calculator. What you should be getting is, so subbing this right hand side straight into the calculator, you should end up getting that T is getting really, really close to 20. Okay, and if you put in a bigger number than 180 here, so if you leave the coffee cool for a longer time period, more minutes, it keeps getting closer and closer to 20. It will never actually reach 20, but it gets closer and closer to 20. So what we can say is that as the time increases, so as time increases, the temperature keeps approaching 20 degrees. So what that means is, as the time goes by, as you leave the coffee there for longer, the temperature is going to reach, it's never going to reach 20 degrees, but it's going to get closer and closer to 20 degrees. So 20 degrees must be the room temperature that the coffee is in, okay? So 20 degrees is simple as that. It must be room temperature. Why? Well, because as you leave the coffee for longer and longer, and I've just tested it by putting in a huge number for T, 180 minutes, remember, is 3 hours. And the temperature gets really, really close to 20. So as your time increases, as time goes by, then the temperature keeps approaching 20 degrees. So it's never going to go below that temperature, basically. It's the minimum temperature that the coffee will reach, or in other words, it's the temperature of the room that the coffee is in. Part 3 then, find the decrease, and they're highlighting decrease so that we don't forget to do that at the end, in the temperature of the coffee 10 minutes after brewing. So they're basically telling us that our time here is 10, and we're going to take our temperature formula, so that's T, and we're replacing every time, every small t with a 10. So that's going to be A is 75. It's e to the power of minus 0.081 times t, which is 10, and it's plus 20. Okay, so you're just putting that part, that can go straight into your calculator, and what you should be getting is approximately 53.364 when you put that into your calculator. Now remember, that's the temperature of the coffee after 10 minutes, but we want to know what's the decrease in the temperature of the coffee. So originally, when it was brewed initially, it was 95, that was the original temperature, and the decrease, it decreases to 53.364. So the decrease, when you subtract one from the other, is 41.636, but we want to round it to the nearest whole number, so that's going to be 42, and of course it's degrees. Okay, just as a matter of interest there, if you forgot to do this part and you just got as far as here, you're still getting the 7 out of 10 marks there that we're going for that question. Okay, part B then. So we haven't come across a whole lot of calculus just yet, but it's more at the end of the question. Part B, so again, it's just reiterating this as your formula. That's the temperature of the coffee at the time T. And the ideal temperature to drink coffee is 82 degrees. Find the time to the nearest second that it takes for the coffee to reach that temperature. So what we're told here is that our temperature, capital T, is going to be 82 degrees. So we're taking our formula, 75 e to the minus 0.081 t plus 20, and this time we're replacing the capital T with 82. That's the degrees we wanted at. We want to find the time. So small t is basically what we're trying to isolate here. And as you can see, it's in the power. So we always know that when it's in the power, we need to use logs to get it out of there. So we've a little bit of rearranging, a little bit of manipulating to do before we do anything. We're going to subtract 20 from both sides, and that will get rid of this 20 here. So that will give me 75 e to the minus 0.081 t. That's going to give me equal to 62. And we're going to divide both sides by the 75, and that will get rid of this here, and it will leave us with just the e to the power of. So e to the power of minus 0.081 t is going to be 62 over 75. And I'm just going to leave that as a fraction. You can change to a decimal if you want. So we're trying to get this t out of here. And because it's in the power, we're going to have to use logs. So we're coming back in with our anti-clockwise arrows. Hopefully we remember. And that's going to tell us that we have log to the base e, and another way of writing that is ln. We're following the arrows this direction, so 62 over 75. And again, we're following the arrows in this direction, equals minus 0.081 t. So this part can go straight into your calculator. And like I said, log to the base e is just ln. And the right hand side is minus 0.081 t. And when you sub log to the base e of 62 over 75 into your calculator, you should be getting minus 0.19035. And I've rounded that up a little bit. So finally, to get t on its own, we're going to divide by minus 0.081. And that should be giving you 2.35. And again, that's minutes. Okay, now have a look at the question. It asks me to give our answer to the nearest second. So a very quick way of doing this, you could find 0.35 of 60 because there are 60 seconds in a minute. But I'm going to show you a nice quick way of doing this. You will see on your calculator a button that looks something similar to this. So it's the degrees, minutes and seconds button, something similar to that. They're in the center there of your calculator. It's the degrees, minutes and seconds button, but it can also be used for time because there are 60 seconds in a minute, the same way as there are 60 minutes in a degree. So when you press that button, it will change this 2.35 minutes into degrees or into minutes and seconds. Okay, so you'll see that it's 2 minutes and 21 seconds to the nearest second. Okay, again, if you get as far as here, the 2.35 minutes, you're losing 1 mark because this part will be marked the same as a rounding error. Okay, so we're getting closer to the differentiation part of this question. So part C, find to the nearest degree centigrade that the temperature the coffee has reached when this is true, where T-T is the rate, so again, that rate of change at which the coffee is cooling. Okay, so the rate of change of the temperature. So the first thing we need to do, well, we're going to write down our formula first of all, and we have that from part B. It's 75 e to the minus 0.081 t plus 20. And what we're asked to do here, we're asked to differentiate it and let it equal to minus 4.05. So when we differentiate, we're going to use our log tables to help us, but the 75, the constant out the front, stays as it is. Next thing we need to differentiate is this e to the power of, okay? And when we differentiate e to the power of anything, well, it stays the same, so it stays as 0 as e to the power of minus 0.081 t, but this is a chain rule question because if you look at your power there, we need to differentiate that as well. So when we differentiate what's in the red box, we're getting 0.081, sorry, minus 0.081. So just to color code it for you, I've differentiated what's in the red box up here, And that's where that part is coming from. And that's from the chain rule. And also when you differentiate the plus 20, that goes to 0. So what we're going to do, just to tidy up before we go any further, we have a constant here, we have a constant here. We're going to multiply those two constants together just so that we can write it as one constant instead. So 75 times minus 0.081, that will give you minus 6.075 e to the minus 0.081t. And we're told in the question that needs to be equal to minus 4.05. So similar to what we did in the last one, t, what we're looking for is up here in the power, so we're going to end up using logs. But before we do, we're going to divide both sides by minus 6.075. That will give me e to the power of minus 0.081. T is equal to 2/3. So when you divide this minus 4.05 by this, you get 2/3. And we're going to use our anti-clockwise arrows, just like we did in the previous part. So we're revising our logs here too. And that will tell me it's log to the base e of 2/3. We're following the arrows in this direction, minus 0.081t. This part can go straight into your calculator. And when you put that in, you should be getting, so minus 0.081t, if I just switch it around, is going to be equal to minus 0.405465. And to finish, to get t in its own, you're going to divide both sides by minus 0.081t. So your t should be working out to be 5. Okay, so your t, your time is 5. And let's think about what that means in the context of the question. So we're basically being told that after 5 minutes, this is true. But we want to know what's the temperature at that time. So we're taking our t equals 5 and we're going to sub that back in to our capital T. So everywhere in our original formula, which was this one up here, everywhere we see a t, we're going to replace it with a 5. So that becomes 75 e to the minus 0.081 times 5 plus 20. And you're subbing that in and you're getting 70 degrees. Now notice, obviously up here, it worked out to be, I think, 5.0057, but you're just leaving it. I've rounded it to 5. Okay, so your final answer, because it was temperature that you're looking for, to the nearest degree Celsius, your temperature was 70 degrees. Okay, and this last part of that question then, so a very good question, and this involves, I'm just going to make a note for you here. This involves related rates of change. So I'm going to show you a nice easy way to do these questions because a lot of people find them quite hard, but hopefully this will help. We've a sugar cube and it's put into coffee. The sugar keeps its cube shape as it dissolves. As it dissolves, its volume decreases at a constant rate. So the minute I see rate, I know it's a rate of change question. X is the side length of the cube, and we want to find the rate of change of X when the volume of the cube reaches that. So I'm just going to draw myself a very rough diagram. I have a sugar cube, something like that, and we're calling the length of the side, we're calling it X. And they're telling us, just to use this piece of information here, we want to find the rate of change, so I'll come back to that in a second, when the volume is 1/64. So what we're going to do, we know that the volume of a cube is just length by width by height. In this case, that's x by x by x, or x cubed. That's going to be 1/64. So to find x, I'm going to find the cube root of 1/64. And that should give us an x value of 1/4. So we're going to be using that later on in the question. But my diagram over here should kind of help with that part. Okay, so it's a very good idea to write down what you know here and what you want. So first of all, what we know, well, this is the only piece of information that we really have as regards rate of change, and its volume is decreasing at a constant rate. The units will often give you a hint here as to what the rate of change is. So centimeters cubed is volume, and seconds is time. So what they're telling us is they're telling us the rate of change of volume with respect to time. So it's always going to be d something for rate of change. In this case, it's dv dt because its volume is decreasing, and look at your units. It's volume and it's time. So our dv dt, what we know is that dv dt is 1 over 64. What do we want? Well, if we have a read of it here, we're looking for the rate of change of x. So that's going to be, again, it's d something. So it's the rate of change of x. And if you're not told what it's with respect to, and we're kind of told here with the t, it's with respect to time. So if you're not told, it's with respect to time. Okay, so that's going to be dx dt. And what I would recommend then, I'm just going to do this in a slightly different colour, I would recommend writing out my fraction with what I know, what I want, and what I'm looking for. So what we're looking for, or what we want, is dx dt. And what we're going to do with that is we're going to take the fraction as it is. We're going to put the dx on top of one fraction, and we're going to put the dt in the bottom of another fraction. What goes in here and here, they should always be exactly the same, so that when you multiply top by top and bottom by bottom, you end up just getting your dx dt. Okay, so look back in your question. So have a look back up here and see what have you not used from the question that we can put in there. So you'll see, well, we don't have a dv anywhere, so we're going to put dv in there. Also has to go here. And then you'll notice, and just to prove it to you, I suppose, you'll notice that what we have here then, if we do top by top, dx dv, bottom by bottom, dv dt, well, those two are just going to cancel out and we're left with dx dt. So that's kind of just a side note here. Okay, I then do the star, tick and question mark method here. So a little bit different than you might have seen. But I put a question mark under what we're looking for, so that's dx dt. I tick whichever of these we already have, so that's dv dt, and I put a star beside what we need to work for. Okay, so this is what we need to work towards finding, dx dv. So if we think about it, what's dx, what's dv? Well, v is volume and x is the length of the cube. So we know that the volume of a cube, so we're going to create a formula that links volume and the side length together. So v, our volume of a cube, is going to be x cubed. So dv dx then is just differentiating. So that should be multiply down by the power, reduce the power by 1, 3x squared. But as you can see from our star here, it's dx dv we want, so it's just a matter of flipping these two. So dx dv is going to be 1 over 3x squared, because remember that sits in an invisible 1. And then we're going to go back to our formula. So back to our fraction. Our fraction was dx dt is dx dv times dv dt. And we're just going to sub in. This is what we're looking for. We now know dx dv is 1 over 3x squared. We know dv dt from the start of the question was 1 over 64. Or sorry, not 1 over 64. Sorry, I wrote that wrong at the very start. That should have been, apologies about that. That should have been 1 over 20. That was that part there. So that should be 1 over 20 from here. 1 over 20. I'm in the wrong colour. So 1 over 20. So top by top, bottom by bottom, that's going to give me 60x squared. And up here, we knew our value of x. It should have been 1/4. So that's 1 over 60 times 1/4 squared. And that can go straight into your calculator. We're getting 4 over 15. Think about your units. It's going to be, so rate of change of x is centimetres, because it's a side, and t is time. So dx dt, your units come from that. Your x is centimetres, whereas your time is t. Now you'll notice if you're looking at a marking scheme for that one, your answer is a negative. And it's fine to do it either way. It's a negative because the volume is decreasing, it's dissolving, so the volume is reducing all the time. Okay, so hopefully this kind of thing that we've done here with your fraction and your question mark, your star and your tick, that is hopefully of some help to you. And I look forward to chatting to you all next week. Hi there, everyone.